Hello everyone, welcome to watch this video with us. In this video, we are going to help you to go through 6 sample questions for the AP Computer Science exams, especially for the question in the AB level, which is advanced level of the AP Computer Science. The first question is about choosing the best data structure for the task. So let's see what kind of problems is in here and what are the possible choices that we have. Okay, a program is to be written that simulates and keeps track of the random motion of a point whose position is represented by coordinates x, y, and the point starts at 0, 0 at time equals to 0. It is to move randomly a large but unknown number of times. A record of its xy positions must be kept so as to be able to recreate any point, any part of its path starting from a given previously recorded xy position. So you can going backward and also going forward. The program is to print the point's xy movement forward or backward in time from the given xy position, and the user also may assume that no point is visited more than once. So we might have to keep track. Now, assuming the existence of a point class that holds a pair of coordinates, which of the following is the best data structure for the task? Okay, what kind of choices that we have? Okay, the first choice is that we might need one-dimensional array of point objects. Two is a two-dimensional array of integers in which the array indexes represent the position visited by the point, and each integer cell of the array is a counter that keeps track of the number of moves to that direction. And the third choice is a circular double linked list of point objects. The fourth choice is that a stack of point objects, and the fifth choice is a queue of point objects. So let's see how we evaluate all of those choices. We can eliminate the choice A because when you mentioned about if we want to use a one-dimensional array of point objects to record the movement of the path of this drawing, then there's one problem because this is only an array of point objects. We don't have additional variables or other data structures to controlling that. We have to assume no point is visited more than once. So we can eliminate choice A because for this part, it cannot be done. Let's see choice D and choice E. Choice D is about a stack of point objects, and choice E is a queue of point objects. We know that from the directional orientation, the property of stacks and queues, we can control the direction. If we can control the direction, then we don't have to worry about we will have one point visited more than once. So, for example, we know that stack is first in and last out, and we know that queue is first in, first out. So if we inserted all those xy positions represented by the class points into the stack, and also then pop it out of the stack, we can make sure that after it popped out, every point will be only visited once, but we can only control the direction with backward directions. For the similar reasons, we can only control the directions of the queue for those points inserted into the queue. Is for the forward one. But for the requirement of these descriptions, we have to print out the points as xy movement forward or backward in time. So D and E could be eliminated too. Now let's take a look around about the B and C. B is a very careful design of the data structure. It fits the requirement of this problem. First, it has a two-dimensional array of integers. And also, the array indexes represented the positions. and each integer cell of the array is counted that keeps track of the number of moves to that position. That would be good, because if we can keep track of the number of moves to that position, and also if we can just using the indexes of the arrays to track the points, then we can make sure that no point is visited more than once. That means if we choose the movement to be forward, we cannot move backward, and if we choose the movement to be backward at the beginning, we cannot move forward. So these choices can guarantee that. But how about the choice C? The choice C is that a circular doubly linked list of a point object. Apparently, this can also be done for the choices. Why is that? We can track the starting point and trace the direction. Once we once we decided the direction at the beginning, then we can just remove the point within the doubled linked list and just try to track for the direction that has not been visited before. For example, if we keep the track on the double linked list and we want to go backward, then we just remove, before removing this point from the doubling linked list, we trying to keep track of its previously objects, the previous points, instead of this double linked list. Then remove it from that. Now the new current position of the point instead of the doubling linked list, because we don't have to connect the new point to the previously point's next position. So there's no way to turn back. The same condition can be applied if we choose to move forward. Once we remove that point and also recorded the current position as forward, that means the next position of the doubly linked list. If we don't carefully manage that, we can only continue going forward. So a circular doubly linked list can also meet such conditions, as long as we make sure that the directions of the forward or backward could be done in time. So comparing to the choices of B and C, apparently it looks like the choice B is a little bit redundant, and the choice C fits the requirement. Okay, so the best data structure for this task is apparently a circular doubly linked list of point objects. Okay, now the following is a series of 3 questions. Questions 2 to 4 refers to the object-oriented programming design concept. It refers to 3 classes. The first class is tennis player. The second class is a good player. The third class is a weak player. So we have 3 classes below, and these classes are used to build a program for simulate the tennis game. Okay, let's read the classes line by line. First, we know that the tennis class is a public class, but also it is an abstract class, which means that we might need to extend this class for fulfilling some functions, some method which might be abstract and has not been implemented so far. Okay, let's see. What are the member variables inside of this abstract class tennis player? It has a private string called myname, and it has a constructor. You only have to input a string name, and this private string called myname will be assigned as the input string of this constructor. Similarly, for the getter, that is called getName, will return this myname. Also, there are 2 abstract methods that related to the tennis player. The first one is serve. it will return boolean, which means that either this player serves in or serves out. And also there's another method called service return, that is a return shot. It also returns the boolean value, which shows that either this return is successful or not. So for all those other advanced players that extended from this tennis players class, it needs to implement the method serve and also service return, but it does not have to modify the method tennis player and also get name. The second class that we're going to read is called a public class good player that extends tennis player. Again, the constructor of this good player also receive input parameter called stream name, and also it has a serve. Note that right now the serve method return with a boolean value. There's no abstract words for this serve method. Okay, let's take a look around for the next slide. The next slide for the post condition is return true if the serve is 80% probability, and false if the serve is out is 20% probability, which means that this is a good serve. That means this is a good tennis player. And for the serve function, again, for this serve function, we want to implement this. For the service return, the return serve function, the post conditions for a good player is that it will return true if the service return is in a 70% probability, and false if the service return is out, that is 30% probability. And also, the abstract words has been removed from the original abstract class, and we can implement, but the implementation here is not shown. Similarly, let's read the third class. It's called a weak player. It also extends tennis player, and it also, from its constructor, it also receives an input stream called name. Of course, it will assign that, but the implementation here is not shown also. Let's see what's the difference between this serve and service return. Similarly, those abstract keywords are removed. So which means that this class, you can construct it the preconditions of the serve for a weak player. It only requires that returns true if the serve is in a 45% in probability, and false if the serve is out, that is a 55% of probability. For the service return, it also has a very less mediocre requirement. That is, it will return true if the service return is in a 30% probability, and false if the service return is out, that is 70% probability. And the implementation is not shown here. Now let's consider what will be our implementation issues. I mean, comparing to the good player and weak players, there are probabilities that has been limited. But how can we guarantee that the serve of these good players or weak players will directly fit into the requirement of the percentage of the probability of their serve and also their return serve? We might need something. For example, like a math class, and also we might need some random number, and we might need the output of this random number to decide the probability. Because notice that the math.random, it will return a variable which is between 0 and 1. It will never reach 1, but it probably will return 0. So we probably can use the math.random variable to limit the percentage, the successful rate of the serve of players, and use this to distinguish, okay, whether this is a good player or this is a weak player, just by the number that it has been returned and cast it, and using some comparison. So how do we do that? First, we will go through this series of problems. Okay, let's see. Question 2. Which of the following declarations will cause an error? You may assume that all the constructors are correctly implemented. Okay, there are 5 choices. First, Tennis player T equals to new tennis player Smith. Oh well, we know that tennis player is an abstract class, so which means that we might be able to create a tennis player, but since it's a abstract class, we cannot initialize an object called the tennis player. So choice A definitely will cause an error. Now choice B, C, D, E, let's see. We already know the answer, but let's take a look around for the rest of the choices. Choice B is that tennis player G equals to new players of Jonas. We know that although the constructors of the tennis players has been built, but since its serve and also return serve method has not been implemented, so we cannot just new an object of it. Again, because the choice B, the good player, and also the choice C, the weak player, both of their serve and also return serve methods are implemented. So B and C will not cause any error. Choice D, it just declare, but it does not initialize anything, and also it does not call the constructor. So of course, it will not cause any compilation error. For choice E, different from the previously four choices, in this time the variable Q has been declared explicitly of a type weak player Q, and also calling the corresponding constructor. And of course, by checking the declaration and also the calling of the constructor, we don't have to worry about such very clear declaration will cause any error. Now let's take a look around of the answer of question 3. Refer to the serve methods in the weak player class. The post conditions of the serve method is that it needs to be returned true if serve is in 45% of probability, and also it needs to be returned false if the serve is out. That is a 55% of probability. And also it needs to implement the method of a serve by such a post condition. Now let's see what will be the detailed issues of our implementation. Which of the following replacements for the /star implementation // satisfy the post condition of the serve method? First, the first choice, one is that we first initialize double value equals to method random. We get a random variables from this random method returned and store it in the double variable. Now the second line is return value greater than or equals to 0 or value less than 0.45. Will this be a good choice? Apparently not, because if you want to controlling the return probability, successful probability of the serve, we have to make sure that for example, if the serve value is less than 45%, the return number is less than 45%, which means that 0.45, then you will return true or false. Then on the other hand, if it's above that, it will return the opposite direction. Now if we return the values which is greater than or equals to 0, or the value which is less than 0.45, then the second constraint will lose its capability to restrain the successful rate, because as long as the value that has been returned by the master random method is positive, then it will return true. So which means that we cannot guarantee that this will be a weak player. If the return value is above 0.6, it might still return true. So which means that this weak player might have a very successful serve rate. Now let's see choice 2 and choice 3. Choice 2 is the double value, which is called method random. We return the value either it will less than 0.45. And also choice 3 is a more expanded version. Because the method random, first then it times with 100, then after time with the 100, it converted with the integer value. Then after that, it cased it into integer called VAL. Now we return either this VAL, the percentage of the return of the random method is less than 45 or not. See, there's except for the scaling, the return values and also the logic of the choice 2 and 3, there's no difference between them. So now let's take our next slide. Okay, which of the following replacements for the implementation satisfy the post conditions of the serve method? I think the answer should be D. 2 and 3 only. Okay, now the last question. The previous question tests our capability of converting and also using the random method, and also test our knowledge about how to using the casting method to round up or round down the value returned by the random method. Now the question 4, the last question, is that consider the following class definition. If we want to define a new class which is called beginner, which also extends a weak player, that means a beginner is a sort of one kind of weak player, and it has some additional variable called private, my cost of lessons, which is of type double. Then there will be some methods belong to this beginner class. Now refer to the following declarations and method in a client program. Tennis player G equals to new good player with name same. Tennis player W equals to new weak player with name Harry. Tennis player B equals to new beginner with name Dick. Followed by that, there is another method which is a give encouragement. The give encouragement method has input parameter called weak player T. Then there will be some implementation not shown. Now, which of the following method calls will not cause an error? So this is about testing our knowledge of the declaration of method give encouragement. Note that the give encouragement only receive a parameter of object type weak player called variable t. So we only have to check the input, whether it will be a good fit for those input parameters of the give encouragement method or not. Choice A, it tries to convert a good player into a weak player. Definitely converted a good player to weak player because there's no extension. So it definitely won't happen. Choice B, it tried to convert a beginner to a weak player. It might also have some problem because the beginner class might override the content of what weak player has. So, for example, maybe the height or the cost. So the choice A and the choice B are in danger. Choice C, trying to cast a weak player to a beginner. Apparently, this will cause an error because if we cast it into a beginner, then the input of this method is incorrect. So that's why we can take easily choice D is will not cause an error, and choice E definitely will cause an error because of the similar reason like choice C. Okay, now let's read question 5. In order and post-order traversal yield the same output of which of the following trees? Okay, this is about our knowledge of traversal methods. Remember that for any subtree, the tracing rule for an in order means that you trace the left subtree first. Then after you finished tracing the left subtree, you trace the current node. Then you trace its right subtree. For the post order, the tracing sequence is that you trace the left subtree first, then you trace the right subtree first. After you finish tracing for both subtrees, then you trace the current node. Okay, so for such a cases, it's had some tricks. Let's see what kind of procedures that might happen. For example, let's take a look around for the in order of the choice A. It will trace A first, then it will trace P, then it will output K, then it will output S. But for its post order, it will trace A first, then it will trace S, then it will trace K, then it will trace P. For choice B, the in order will first trace S, then it will print out K, then it will print out A, then it will print out P. For similar reason, the post order for choice B, it will print out S, then it will print out K, then it will print out A, then it will print out P. So the choice is B. The in-order and post-order traversal yields the same output for this following tree, especially when the tree is a skewed tree with no branches. Okay, now let's see the answer to question D. The worst case runtime is never bigger of n2 for which of the following sorting algorithms? We have merge sort, we have heap sort, we have quick sort. We know that the worst case of a heap sort will reach n squared, but the worst case for merge sort and heap sort will only reach n log n, so the choice will be D.